that for software engineering. That's design patterns we're going to talk a little bit about maybe at the end of the course, but we're not going to be doing design principles for, not for this test anyway. All right. Hello, everyone. Welcome back to Comp 2150, Object Orientation. Today, I would like us to kind of stop building up our C++ example and spend a little bit of more time really just thinking about and applying some kind of weird things that we can do in C++ that we can't do in Java. I also want us to spend some time thinking about the heap versus the stack. And we're going to take a bit of a digression. We're going to take a bit of a digression from object orientation into operating systems. Because I want us to be able to think a little bit about the heap versus the stack in terms of what an address space layout looks like. So what I mean by that is I want us to be able to visualize, and I want us to be able to see what a program kind of perceives memory as it's executing. I want us to see this in relationship to kind of like where objects are being put based on how you're initializing them. So using stack objects versus dynamic allocation of objects, I want us to get a sense of where in memory these things are going. I also want to do a little bit of review. I promised to do review today, so I want to do some review today. And then time permitting, there's some new stuff that I want to talk about where, again, like I said, we're starting to think about the kind of weird stuff that we can do with C++ that we can't with Java. So it's going to be a little bit of like a compare and contrast, and then a little bit of a, let's see how this actually works. Let's run it, let's write it, let's run it, and see what happens when we do this. So it's going to be a little bit of like predict the output style sort of thing, but it will make the point that I'm trying to make. So we're going to do a review first. That's, I think, probably the biggest things on your mind right now. So let's do the review first and make sure that we actually have time for that. The worked example in C++, I think that we'll take a look at the code that we've written and kind of remind ourselves of what all that looks like. And then I'm going to show you some slides that demonstrate some of the things that we can do with C++ that you can't do in Java, because I don't have a good use for them in the worked example that we've got. And that should tell you a little bit about how kind of obscure these topics are in terms of how often you should be thinking about using them in C++. I want us to visualize the stack and the heap, and then I want us to look at, some kind of different things that are related to class hierarchies in C++. I really wanted to do this. I really wanted to do this. We did this idea of scrolling way up. We did this idea of reading the error message. And then I tried to do ChatGPT, and it was just like, no, this system's overloaded. The system's overloaded. So I came today with a tab that was preloaded so that, oh no. Okay, good. Okay, crisis averted. I came today with a preloaded example because I wanted you to see like what this can do. Maybe you've done this on your own already, but I was amazed. Like I don't know how I can communicate this effectively. I am just like shocked at how good this was in terms of helping me debug these errors. So this is the first mistake that I made. Don't forget to include string in one of the classes that I was working with. And the message that I asked it was, why am I getting this error in C++? And like copy paste the error message, and it just told me, indicating that STD has not been declared, but it's being used. This error occurs because you've not included the necessary header file that includes the STD namespace. In this case, you need to include string header file in your source code. And that's amazing. I really think that's amazing. I think that's amazing. But then I asked it the next question, which was this one. why am I getting this error message? And this was, remember, I didn't change the makefile. I didn't set up the dependencies correctly in my makefile. So we had the declaration of that constructor function, but when we tried to do the linking step, it couldn't find it. And this is the answer that it gave me. And this is more dramatic when it's like typing it out as you're sitting here and watching it. But there's a bunch of things about this that I find fascinating and just super impressive. The first is this was that barf that I pasted into it. Like, this is what string ultimately resolves to in C++. And it took that message and it shortened it a lot. And it's like, here, this is maybe what you were looking for. It figured out that this long list of namespaces and stuff is actually std string. Then it told me, well, maybe you didn't declare this constructor. Maybe it doesn't exist. That answer is wrong. That answer is not true. I did actually declare that constructor in the class. So that answer itself is not a good answer. This is a good answer. The constructor has been declared, but it hasn't been defined in the implementation file. That is a conceivable reason why I would get this. I have in my .h file listed this specific constructor with this signature, but I haven't actually written out the implementation of that in my CPP file. And this was the actual reason. So like from that one line of output from the compiler, from the linker, it was able to say like, hey, it's probably not actually being linked in properly when you're trying to compile this thing. And then it tells me, yeah, to resolve this error, you need to make sure that the constructor is declared and defined and that the implementation file is linked properly with main during compilation. I don't know about you, but I am like legitimately amazed by this. I'm legitimately amazed by this. This is maybe like one of those things where I mentioned going to the zoo last class. I take my kids to the zoo a lot because it's a good place to go when you got kids. I take my kids to the zoo a lot and we're just like, hey, wow, look at those polar bears. That's amazing. And they're just like, whatever. Polar bears have always been there. And maybe this is me right now. Wow, this is really amazing. This has always been the case, but I don't know. You don't have to be amazed, but I'm amazed. Okay, thank you for listening. Let's do a review. So I've got a bunch of questions here that we will work through together and we will describe and talk about. But let's have a little bit of fun when we're doing it. Oh, and for the records, there was a question that was asked just before class, but I figure I'll answer it just broadly for everybody. The question was, why not Rust? The question was, is the solid stuff going to be on the test? The solid stuff is not going to be on the test. That's kind of something that I'm pulling down a little bit from software engineering, so you don't have to worry about solid stuff for this test. Evil Franklin. Oh no, my nemesis is in this classroom. It's just one of those cases where if I happen to like, bump you, will explode like matter and antimatter, something like that. Okay, I'm gonna click the start button, but the game pin should stay up throughout. Okay, good. So for the most part, we're in the right spot. Let's talk about each of these and make sure that, that we know about all the different flavors of what we've got here. So static typing, remember in terms of like options that we have for typing, there's two categories. There's static typing and there's dynamic typing. Static typing is the type that a variable is bound to at compile time. So static here means this part is not going to change. This is the type that a variable has been bound to at compile time. Dynamic binding is the type that a variable is bound to at runtime. So when the program is running, when we assign a class type to this, when we assign an instance of a class to this variable, this is going to happen at runtime, so it's dynamically typed. Python is a good example of a dynamically typed language. There are no static types in Python. The variable that, the value of variable is bound to at runtime. This is dynamic value binding. So this is where we're actually saying that at runtime, we're going to assign a specific value to a variable. And then likewise, the value of variable is bound to at compile time is static value binding. So static at compile time, dynamic at runtime. That's the main distinction between the two of those things. Good. Good. This is a multi-select, so pick multiple things, please. Okay, good. So option 1 here, the red option, the triangle, class X extends Y. This is kind of mixing up Java and C++. This is mixing the two together. It's mixing the two together because there's no public. There's no public, and we don't put public on our class types in C++. We don't use the extends keyword in C++, but we do use it in Java. And in Java, we don't put the semicolon, but we do in C++. So this is kind of like, yeah, red herring mixing those two things together. The blue diamond option here, this one I see is this, I guess, after the first two correct ones, the third most selected option. This is also a red herring. So let me, oh gosh, a red herring is an idiom. A red herring is like something that looks interesting or something that looks like it might mean something, but doesn't actually mean anything. So when you're reading a story and you have a red herring in the story, the author might be telling you in detail about this specific thing, but it's actually completely irrelevant to the actual story that you're reading. So the 2 colons there, that's a red herring in this case. When we're defining methods and when we're defining things for the class, we've got our class declaration in the header file. And when we're defining things in our CPP file, we're using that 2 colon syntax to say, this method is being defined for this class name. We don't extend classes this way, though. So we're not using that 2 colon syntax to do it. The yellow option, this is the way that we have seen our extension of classes in C++ so far. So this is the one that that's correct, I guess. C++ also has support for multiple inheritance. This is something we haven't talked about, but I'm going to mention today. I'm going to mention it today and then not really talk about it much because it's not a good feature. It's not a good feature. It's a feature that the language has, but I don't even have a contrived example to show you because I don't think it's that important or that useful. And if you find yourself trying to do multiple inheritance, it's not a good situation to be in. But if you do use this comma syntax, now what this is saying is that class X extends both Y and Z. So that's what that is saying. So those two options are correct. We're good. Keep moving. Good. Okay. 31 stays at the top. Okay, good, excellent. Dynamic dispatch. This is also called dynamic message method mapping, dynamic message to method mapping. There's that keyword dynamic again, which is to say that this is something that's happening at runtime. This is happening at runtime. This is going about looking at a class hierarchy and then looking at the actual type that an object has at runtime, the actual instance of the class that it is at runtime, and then working your way up that hierarchy to decide which class should respond to the message that's being sent. So if you have a toString method that's at the bottom of your class hierarchy, it might be invoking that one at the bottom, and it might work its way up and bubble up to the top, all the way up to object to decide which one to run. Dynamic dispatch, this yellow circle answer here, how to cast an object to the right class at runtime. This does have that runtime keyword, and it is related to kind of thinking about relationships between classes, which is where we're thinking about casting, but it's not this. The the blue diamond here, which class is used at runtime? Again, this is kind of a partial answer, but this does apply to C++, so that kind of invalidates this option for sure. And the deciding which of forward declaration or include to use at programming time, the keyword dynamic makes this one not the right answer. So we've got the green square here. Which method answers a message in a hierarchy at runtime? We're good. Yeah. So the question is, isn't the method stored in a class? So dynamic dispatch is something that does happen in C++. And this is very directly related to polymorphism. So when you have multiple classes that are related to each other in a hierarchy, so class X extends class Y, when you call a method on an instance of an object, regardless of what type it is, you're looking at the actual value that it has at runtime and then deciding based on that whether or not there's a method in that implementation that matches that signature or that method, or the message, sorry, and then working your way up the class hierarchy. So it doesn't really have anything to do with classes and methods being stored in a certain way. Am I misunderstanding your question? Yeah. So, but it's very specifically at runtime. So when you're saying the word class and how things are stored, I guess make sure that you're talking about the difference between runtime and compile time. When I heard you talking about how the class stores the methods, I thought at first that you meant maybe at compile time specifically and not at runtime. So when you're communicating about that, just make sure that you're making it clear what you're whether you're talking about compile time or runtime when you're writing answers for a test, for example. Okay. Okay. Any other questions? We're good. Keep going. Okay. "31 stays at the top." Rashid has a streak with 3 correct answers. Great, good, good, excellent. So when we're thinking about access modifiers for instance variables, whether they're in Java or C++, so this applies to both languages, the most appropriate access modifier to choose by default is private. So this is your default option, choose private. If you come up with a compelling reason to choose something else like protected or public, then you can make that change, but by default, your option should be private. Abstract is not an access modifier, so this one is kind of taken out of the running. I picked this picture specifically because I thought it really, visualized the idea of private access modifiers. I'm going to laugh at my own joke. Ha, ha, ha. OK. I'm just going to say this question, and I want you to verbally answer this. So private is the most appropriate access modifier for instance variables. What's the most appropriate access modifier for methods on a class? I'm going to do 1, 2, 3, and then I want everyone at the same time to say it, please, after 3. So on the beat after 3, so we're on the same page. 1, 2, 3. Thank you. Good. Public. Excellent. So private is the good default for instance variables. Public is a good default for methods. That's not universally true. So just to clarify, it's not universally true that methods on a class should be marked public, but if you ever need to use them outside the class, then yes, they should be marked public. Wow, OK. I really honestly think this is the first time that I've seen somebody stay at the top just the whole time so far. I'm trying to jinx it. I'm really trying to jinx it for other people. Not really. OK, great, 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 great. So include and forward declaration are two different ways that we've been trying to use classes that are related to each other. And this is specifically in C++. I'm just going to really quickly pop open my VS Code here. And I'm going to take a look at Pokemon.h. This is a bad example because I'm actually going to delete this. Forward declaration is happening here on line 4. Forward declaration is happening on line 4. In this file, Pokemon.h, we don't actually need to know anything about trainer. We don't need to know any of the methods that are encoded in it. We don't need to know any of the instance variables that are in it. All we really care about is that a class by that name exists. The only place that we're using this in Pokemon.h is to have this property, this instance variable that is a type of pointer to that class. That's the only way we're using this file or this class name. In that sense, the most appropriate way to use it is to declare it as a forward declaration. So use forward declaration here if we're only ever going to use a pointer to that thing. In Pokemon.cpp, here, I am still also not using trainer, so I never actually have to include it. Let's take a look at trainer.cpp. Also not ever using Pokemon. Here I am. So I'm doing toAddGetNickname. So I'm calling a method on a Pokemon. Because I'm calling a method on an instance of this class, I have to know what methods are available on it. So I have to use number include to get the full definition of the class, the full declaration of the class. Good. Keep moving. Yeah, yeah. So you don't need both. So the question is, do you need both or just one? If you're only going to need a type, so you only need a pointer to a type, then you shouldn't do number include and forward declaration, because they both kind of accomplish the same thing, and you should do as little as possible. It's kind of what we're striving for here. If we only ever need to know that there's a type, then we should only ever declare that there's a type available for us to use. If you actually need to call the methods, then don't do forward declaration, just include the whole class. Okay, is there another question? We're good? Good, 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 good. We got 2 more questions here. Oh, wow, okay, good, wow. Okay, awesome, great, good. So include one or more methods. That I think that's just not something that anybody picked. So why am I dwelling on it? Nobody picked that, so that's good, excellent, great. Include one or more pure virtual methods, and then the other one that looks reasonable is include one or more virtual methods. In C++, there's a distinction between a method that is abstract, so it doesn't have a definition in the class that it's declared in, and a method that can be overridden by a subclass. A pure virtual method is one that has no implementation in the class that it's in. It's explicitly abstract. There is no implementation of this method in this class. A virtual method is one that a class is saying, subclasses of me are allowed to override this. They are permitted to override this method. Methods that are not marked virtual in C++ cannot be overridden. You can't override a method that's not marked as virtual. You can give a method that's the same name, but you'll never actually get to be able to use it. So a pure virtual method is one that doesn't have an implementation, and the presence of one or more pure virtual method makes the enclosing class, the thing that contains this, an abstract class itself. You cannot create an instance of a class that has a pure virtual method. In C++, there is no abstract keyword. There's no abstract keyword for us to use, so we can't do that. That's true in Java, but it's not true in C++. We're good? Yeah. So a class in C++ can declare a method as pure virtual and provide an implementation, yes. But typically you wouldn't do that. That would be a very strange thing to do. C++ seems to have this, I don't know, this motto of, that's strange, but let's do it anyway. A base class that has a pure virtual method probably shouldn't implement it. But the mere presence of it says that this is abstract and you can't make instances of me anymore, even if I do provide an implementation of it. There's another question at the back. Anjam, you okay? Okay. Any other questions? We're good? Good, 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 good. Good, okay. Okay, wow. Here's the last question. Okay, good, good, great. I really love the kinds of pictures you can find when you use the word virtual in your search terms, and just the like bizarre things that people are doing while wearing a headset. It's, I don't know, the last couple of years have just made this a very wealthy kind of niche area of photography. I don't know, but I'm delighted that these pictures exist. How do we make a pure virtual method in C++? What's the syntax to do that? This is close again, but it's a red herring in that it has that abstract keyword, and there is no abstract keyword in C++. This is not something that we can use. This is close. So this one was, I mean, this is actually, I forgot to put the parenthesis on here, but this was a question that somebody asked, and he's not here today, and that's okay. What happens if we use some other modifier? So I looked this up, and it's actually the literal equals 0. So it's actually literally just equals 0. It's nothing else. It's just the presence of equals 0. There's no assignment. It's just the presence of these two symbols, equals and 0, that marks a method as a pure virtual method. We're not actually doing an assignment here. This is the implementation that is correct. Virtual int method. This is a virtual method. This is one that can be overridden, but it's not a pure virtual method. So it's not making the class abstract. Good. Good, 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 good. Excellent. Okay. Outside class. Okay. I can't tell if that's somebody that's not here or if like sitting in the hallway or something. 31. Okay. Congratulations to 31. Okay. So before I start talking about new stuff today, where new stuff is not on the term test, I want to give you a chance to ask me questions that's not me pointing questions at you. So if there's anything from the last, I don't know, 5 weeks, 4 weeks that you have any questions about, please feel free to ask. Yeah. So the question is, do you have to be up to date on your data structures knowledge? My answer to that is that's a reasonable thing for us to ask you on an assignment. It's not a reasonable thing to ask you on a test. I assume that answers your question. Yeah. Yeah. Sure. So the question is to ask a little bit about messages and calling with methods. And I'm actually just going to pop this up, and I'm going to explain with this example. So this is an implementation of the trainer class. When we call methods on another object, we've got two things that are interacting here. There's the object that is the sender of a message, and there's the object that is the receiver of a message. In this case, the sender of the message is the enclosing scope. The enclosing scope here is an instance of the trainer class. So we have an object that's an instance of this trainer class. It is sending messages to this object that's called toAdd. toAdd is a type that is a pointer to Pokemon. The message that's being sent from the instance of the trainer class is the getNickname message. That's the name of the message that's being sent. The receiver here is the toAdd object. There's no hierarchy here, so the message to method mapping is just directly, we have this Pokemon type. There's a method in it that's called getNickname. That's the method that gets invoked when we send this message to that object. When we have, I'm going to go to main.cpp here. When we have this structure, we've got an object here that's called myPotion. Its static type is a pointer to item, and its dynamic type is potion. When we call the apply method on myPotion, we're actually going to do a method to message to method mapping. The message is apply. The method that we're trying to find is in the hierarchy that is below this class. So we're looking at the runtime type, which is potion. Potion has an apply method, so that's the one that gets invoked. And we don't go up the hierarchy to the parent class to get that. So it's about translating the name of the method into the actual method that we're invoking. Does that? In this case, the sender is like, the enclosing scope is main. There's no object here anymore. It's just going to be some nebulous idea of what the main function is in this case. And the receiver is myPotion. So the receiver is almost always going to be the thing that you're calling the method on. So what method you're actually trying to call. The sender is going to be the enclosing scope. And then when we go between objects and functions, we get into this weird state of there isn't really a sender in this case. The sender is whatever the main function is. Is that okay? Okay. Let me go back to Pokemon. It was trainer, right? This part? What part of this, the or equals itself, or? Okay. So I'm going to actually break this down into a couple of parts. So we're doing several things here. We're saying bool names equal is equal to add get nickname. And we're asking, is it equal to this Pokemon at I get nickname? So this is our Boolean expression, okay? I want to make sure I'm answering the question that you're asking. Is this the question that you're asking? Okay, I'll just keep going, and I just don't want to make sure that I'm not answering a different question than you're asking. But when I'm finished, I'll revisit you. Okay. Okay. So the expression here that we're really asking is the current Pokemon that we're looking at, is it equal to the nickname of the Pokemon that we're trying to add? So we're scanning through the entire array of Pokemon that this trainer has, and we're asking for each one, is it equal to the nickname that we've got? The next part is to say duplicate is equal to duplicate or names equal. So this one statement here is kind of saying the same thing. Duplicate is false by default. So when we enter this loop, we've got false. We inspect the first Pokemon and we test to see if their names are equal to each other. And if this is false, they're not equal to each other, the names are not equal, then the OR expression here is going to evaluate the false or false, which is false. That's right. So once it becomes true, it stays true. So if we're halfway through our list of Pokemon and one of them happens to have the same nickname, so at I is equal to 3 and we have 6 Pokemon, then duplicate becomes true because we're going to say false or true. And then because it's true or whatever, it will always be true after that. Okay. Okay, good. So I think I was thinking the same thing that you're asking. Okay, good. The test is on paper, so please bring a pencil. Yeah. Sure. So I mean, the bottom line that I'm going to say is that blindly put pragma once on your header files. That's the bottom line of all of this, is just put pragma once on your header files. The idea here is that if we have this circular dependency, and so Pokemon and trainer have a circular dependency on each other. So let me pop open trainer.h here to the side. Pokemon has a dependency on trainer because we're keeping track of the original trainer. And trainer has a dependency on Pokemon because a trainer has an array of Pokemon. The dependency that we have here is that we need to have the instance of that class available to us so that we can use it. So we've got a circular dependency. That's the setup. When we're doing includes, the issue that we have with saying include trainer.h, and then over here saying include, I'm going to revert this, but Pokemon.h, is the way that our preprocessor works. So everything that's number sign whatever, this is our preprocessor that's happening. It's operating purely on text. It doesn't know anything about C. It doesn't know anything about C++. You can use a preprocessor to generate like plain text files if you wanted to. That would be something you could do if you want. I don't know why you would do that, but you could. If we don't have pragma once, what this line here says is literally just copy paste the whole thing over here in line 4. And then we start all over again. So this is being applied recursively. When we go up here, now we have include Pokemon.h, which is just a self-reference to the file that we're looking at right now. So it's just copy and paste that entire file in there, which includes trainer.h, which includes Pokemon.h, which includes trainer.h. The pragma once there is saying, if I am attempted to be included multiple times, so if the preprocessor then is keeping track of which files it has already included. If it's attempted to be included again, it's a no-op. So thinking of 2280, I don't know if you do no-ops in 2280. Instructions that don't do anything in an assembly language. Basically, just don't do it again. So pragma once says, if I am trying to include a file that's been included before in this attempt to compile this thing, don't include it again. Does that answer your question? Okay. Okay. Yes. Yeah. So this is just a variable that's named Ash. This is a variable that happens to be named trainer. Make it me. The difference between the difference that I'm trying to show with these two lines is that one calls the null constructor, the one that takes no arguments, and that's the first one where we don't put any parenthesis after it, and then the other one calls the constructor with one argument. They're both stack allocated, yes. Yeah. Find the bug, find the compile bug in the code. I can say with certainty no. If there's a compile bug in our code, it's a mistake and not, we're not going to be asking you a question to find syntax errors. You're not a compiler. We have tools for that. We got tools for that. That's not a good skill to test. Yeah. Sorry, can you repeat that, please? Will you be tested on stack and heap variables? So in the sense that this was something that I did talk about last class, and specifically how to use the difference between stack and heap, so the dot versus the arrow, that is eligible for testing, yes. The stuff that I'm talking about today, where I'm kind of trying to visualize stack versus heap, no, that's not part of the test. All right. Awesome. Okay. We're going to do great on the test. We're going to do fine. We're going to do great. The test, remember, is 50 minutes. It's going to start when class starts, or as close to as when class starts as possible. And then after the test time is up, I'll stick around in the classroom if you have questions for me. But if there's nobody here, then the class is just over. I'm not going to teach you stuff after you write a test. That would be, nobody's going to learn anything. That would be a waste of everyone's time. So after the test is over, we're just done. And then you'll have a great weekend. Yeah. Okay, so let's get a move on here. The example that we have been building up in C++ for quite a while now is our little Pokemon kind of game. It's a terrible game, but it's a game. It's the start of a game. We're building up the data model, and we're trying to build up the interactions between the different classes that we've got, mainly as a way to motivate some of the features in C++ that we want to explore. We have now used strings in a C++ program, and the biggest difference between strings in C and strings in Java and strings in C++ that we have been able to use with C++ is in trainer.cpp here, where we are able to use double equal sign to do comparisons between strings. That is the biggest difference between the other two languages that you know about. In C, you have to go through the characters in a loop or use stir equals. In Java, you have to use the equals method to compare two instances of strings because they are objects. In C++, you can finally just use the two equal signs to compare two strings and two objects to each other and be able to get the result that you're expecting out of it. We're able to now create a class hierarchy in C++ with inheritance and polymorphism. And the way that we did that was by using that item and potion example. So we went to our Pokemart and we bought a couple things for our Pokemon. And we declared item.h, which doesn't have anything in it right now. It doesn't have anything in it. All it has is a pure virtual method that's called apply. And what we're doing is taking a Pokemon as input to this method in this hierarchy, and we're doing something to that Pokemon, that instance of Pokemon. The different subtypes that we could declare from this, the different things that we can have an effect on a Pokemon, would change the Pokemon in different ways based on the type that it is at runtime. The long-term goal here is to have a list of items in our trainer and to be able to just use whatever items that we have and apply them to arbitrary Pokemon without having to think about them. We created abstract classes in C++, so this is our item class. We've started to talk about stack versus heap allocated objects in that we can use them. We can declare a stack allocated object. We can call methods on a stack allocated object. We can declare and use heap allocated objects using the dot and the arrow operators as differences between them. The one thing that we haven't done is visualize this relationship and where these things are actually going in memory. So this is what I want to do today. I don't think we're going to be able to do this, and I'm just going to leave it. If there's a strong desire for this, if there really is a legitimately strong desire, please send me an email, and what I can promise to do is like make a little tutorial video just separate from class material as opposed to me stepping through LLDB in class. If we have time, I'm going to build a list for our items and for our potion. But given what time it is right now, I don't think we're going to be able to do that. And I think that I might be leaving this as an exercise for the reader to build a list type in C++. The structure of the list type that we would be building in C++ is very close to the list type that we were doing in Java. I want to just go through a couple of things that you can do in C++ without providing an example of demonstration of it, because I don't have a good example of demonstration for it. The first one is that C++ gives you the ability to have multiple inheritance. When you're writing code in Java, you're limited to having exactly one class that you can extend from in your hierarchy. Object is at the bottom, the top of your tree, and it's a tree. It is a pure tree. You go from the top, and you can have one parent, and one parent can have multiple children. In C++, you can have multiple parents to a single class. So this example here is we have this potion type, and we have two other super types, an item type and a healable type. This means that the class potion has two parents, item and healable. The big problem with this that Java is trying to avoid is that if two parent classes have the same signature and they have virtual methods with the same signature, so they're marked as methods that we can override, which one do we use? It's unclear. If we have item that has apply and we have healable that has apply, and they're both marked as virtual or they both have implementations, which one do we use? We may spend some time later in class thinking about this, but for now, know that this idea exists, that we can have multiple inheritance, and that there are problems with multiple inheritance. And it makes it difficult to think about which method or which variable is going to be referred to. I don't have a good example of needing this in the contrived example that we've got either, so I'm going to just verbally describe it to you. In Java, we have this idea of being able to ask what type an object has at runtime. The way that we ask what type an object has at runtime is using that instance of operator. We put on the left-hand side the thing that we want to know the type of. We put on the right-hand side the type that we're asking if it is of that type. And if it is of that type, then we can safely compile it. There's a compile error in my code here. In C++, there is no instance of. There's no instance of. There's no way for us to ask this question, is this class a subtype of another class? The only way that we can ask if a type, if a class, if an instance of a class, if an object is a subtype of another class, is to call a method, to call a function on this thing and just try to cast it. Just blindly try to cast it to another type. This dynamic cast function takes in its angle brackets the type of the thing that you want to cast it to. And then in the parenthesis is the actual object that you want to cast to that type. The method returns a pointer, and it can return one of two things. It will either return a pointer to that type, so it will return a cast instance of that thing that you have in the type that you asked it to be converted to, or it returns null pointer. And that says, no, I couldn't convert this to this type that you asked me to convert this to. It's not an instance of this type, so I can't actually do that. So there is no instance of in C++. You have to blindly try to cast it and then check to see if it's null after you did blindly try to cast it to see if you were able to successfully cast it or not. And this is a summary of something that we talked about during that Kahoot, but when should you use forward declaration versus include? Include is necessary when you need implementation details of the class that you are using in whatever it is that you're trying to use it in. So examples of that are if you are extending a class, you have to know about the class's implementation to extend it. If you're implementing a class, so if you have a CPP file and you're trying to implement the methods for a class, you have to include the class definition in the H file. And if you're calling methods on an object, you must include that header file because the place where you're calling it needs to know about what that method is that you're trying to call. If you only ever need a pointer, then forward declaration is sufficient. You don't actually need to include the entire thing if all you ever need is a pointer. All right. So we've got two different kinds of variables. We've got two different ways to store variables in our C++ program. We've got stack variables and we've got heap variables. This concept is present in Java. There is a concept of stack and heap in Java, but in Java, all instances of classes are on the heap. Everything is on the heap. Everything is dynamically allocated. Primitive types, integer, char, boolean, these are always stack variables. They're always stack variables, and they're always passed by value. What I'd like to do is visualize some stuff. I'd like to visualize an address space layout. This is a fancy way of saying I want to know what memory looks like internally. When a program is running, I want to know what a memory looks like. I want to be able to see in this layout where the heap is located. So in physical memory, where is my heap located? I want to know where the stack is located. And I want to know how they change as code is running. So what's being changed in the stack versus what's being changed in the heap. I'd like to motivate this by taking a look at this code here. And I'm going to share a link with you just quickly here to a textbook for operating systems, because this is where you're going to find more information if you're interested in this. The textbook that we use in operating systems is called Operating Systems, 3 Easy Pieces. And it's free. You could go download it now if you want. You don't have to buy it. The part that we're talking about right now is chapter 13. It's this address spaces idea. And I'm going to skip past some stuff because this is not operating systems. This is our visualization. I'm going to draw this out. I want to draw this out. And I want to see how this idea changes as the code is running, as the code that we have is running. So let's take a look at our program here, our little sample program. And I'm going to pop open my tablet here. And let's draw this out. So we have this program that's running. It has a main function. When a program runs, this program has access to memory. It has access to memory. Typically, what our operating system is doing when we have a program that's running is it kind of breaks main memory into a few different parts. This is the top of memory here. So this is at, I'm going to say 0 kilobytes. And this is the bottom of memory here. So I'm going to say lots of kilobytes. So like, 16 gigabytes or whatever it is that you have in your machine. When a program is running, a program consists of instructions. The program itself is code. It has to be in memory to be able to run. It has to be in memory to be able to run. Our address space is laid out such that the code, this is our program's instructions, is at the top of memory. So top of memory being closest to 0. Immediately beneath that, we have this region of memory that's called the heap. And then at the bottom of memory, we have our stack. As a program is running, the heap always grows downwards. So as a program runs and we try to allocate memory in the heap, we're always adding to the bottom part of the heap. We're always putting at the end of it there. And as a program is running, we always add to the stack at the top. It grows upwards toward the heap in the code segment. when our program starts, so we've got this program that has just a main function in it. The main function is a method. Sorry, it's a function. The main function is a function. The main function is a function. The main function is a function. When a function is called, we get put on top a thing that's called a stack frame. The stack frame is going to be memory that consists of where the address of this thing is, and then also all of the memory that's necessary for stack variables. So the stack frame that we have for main here has memory that's been allocated for this object that is called me. It has memory allocated for this object that is called you. These are both stack allocated objects. It has memory allocated for this variable that is called q. But I'm going to put an asterisk beside this. And it has, I'm sorry, that's not q, that's p. It has memory that's allocated for this variable that's called p. And it does have memory for this variable that's called q. In the stack frame, this me object is the entire thing. So that whole object that we have for type trainer, and type trainer here has a name, it has an array of Pokemon, it has an int cur Pokemon. There's space for all of those put into the stack frame. So that entire thing is stored within that. The object P here, this, the only thing that's in our stack frame is enough for a pointer. That's all that's there here. This is a single pointer to something. Only enough for a pointer. That's really tiny. That's really, really tiny. This is only enough for a pointer. So P is a pointer to something, and we are making an assignment. We're making an assignment here that is new Pokemon. We're calling that constructor. But all that we have in the stack frame is enough to store the pointer itself. The other objects that we have there, it's the entire thing. The whole thing that we have in the class is set up and ready to go. For new Pokemon, what we've got here is this is going to be allocated in the heap. So when we say new Pokemon, if we're thinking about this in terms of what C++ is doing, if we're thinking about this in terms of what C was doing, a C translation of this is something like malloc size of Pokemon. This is going to take a chunk out of this, a Pokemon-sized chunk out of our heap, and add it to the bottom. And we've got, again, enough space here for what our Pokemon is. So it's got a nickname, a type, and HP. If we were to take this and start printing out the addresses of these different things, we're going to see addresses that kind of fit into this structure. The things that are allocated on the stack are going to have the highest addresses. The things that are allocated on the heap are going to have lower addresses. And if we were to print out the address of the main function, it would have the lowest address in all of the things that we've got here. You may have seen a little bit of this in 2160. You may have seen a little bit of this in 2280. You will definitely see this in 3430 in operating systems when you get there. If you're interested in taking a sneak peek at what's going to happen in operating systems, I'll put a link up to this textbook on the course webpage. If you want a sneak peek, if you're bored in the summertime, you can read this textbook a little bit. But this is broadly what's happening when we're allocating stack versus heap variables and approximately where they're going in our address space layout. We'll put a copy of this diagram up on the course webpage, so you've got it. I think I'll move on. All right, so we've got a few minutes left. I don't want to spend a lot of time on this because I don't want to just dump a bunch of stuff on you and say, don't worry about this until term test 2. So let's just take a quick look at this, and then we will leave this until after this week is over. We're going to start talking about how classes and methods are related to each other in terms of a class hierarchy. We're going to be starting to think about this in terms of formal definitions and formal terms to describe the ways that we can change and replace existing behavior in classes by extending them. And we're going to be talking about this in formal terms in terms of how we can change and replace instance variables in classes as we're extending them, and the kinds of behaviors that we can have in C++ versus the kinds of behaviors that we can have in Java. Let's start by thinking about the stuff that you know already. When you are replacing methods in a parent's class, so you have a class that is extending another one, and you're using either new methods, additional methods, or you're trying to replace existing methods, what are the ways that we can make changes to a parent class? The stuff that we know about right now is that we can extend a class and then don't do anything. We can have a x extends y and then don't actually do anything by adding any new methods to it. We can have this extension that doesn't actually do anything to a superclass, and it only adds properties. So adding instance variables and not doing anything else to the other methods that we have there. The other way that we know about how to change things is to add new methods. So we have x extends y, and we are going to add new methods that are in the subtype that are not defined in the supertype. So a completely new set of methods on the subtype. This is stuff now in terms of replacing method names that we might have a vague idea of. We might have used some of these properties before, but we didn't necessarily have names to describe what they were. We can replace a method from a superclass. And you have definitely done this before. You've definitely done this before, thinking about C++ and thinking about Java. When you name a method the same as it is in the superclass, you're overriding it in Java. In C++, if it's been marked as virtual, you can override that behavior in the subclass. The two ways that we haven't talked about are shadowing methods, shadowing functions, and redefining methods or functions. The other way that you can replace behavior in a superclass is to refine the behavior that's defined in a superclass. And this is kind of a semantic difference between replacement and what you're doing with replacement. Replacement is just replacing entirely. So taking a method and using the same signature and overriding. Refining a method is still doing that, except you call super in the method itself. So you're using the existing behavior in the super class to do something, and then you're changing it slightly in the class implementation that you're looking at right now. I'm going to stop here. I'm just going to completely stop here. And I'm going to skip ahead, and we will look at this next week. But at this point, I think that you should be able to create a moderately complex set of classes in C++ that are related to each other. You should also be able to visualize an address space layout, thinking about where the heap and the stack are located and how they are related to each other in terms of what happens when we're calling methods, when we're using dynamic memory allocation versus just allocating things on the stack. And this one you can't do yet, but we will do this next week on Tuesday. Thank you all for coming out, and I will see you on Thursday. Bye, everybody.